everyone, and welcome to today's SEG webinar. My name is Deanne Ryder, and I am the SEG webinar coordinator, and I will be moderating today's webinar. I first wanted to cover a few logistical items. Today's call will be listen only for participants, but we encourage you to ask questions during the webinar using the Q&A button in the control bar that should appear either in the top or the bottom of your screen, depending on your setup. Questions will be answered at the end of today's presentation. The presentation will be recorded and an archive will be available following the event on the SEG website as well as the SEG YouTube channel. If you've missed one of the previous webinars, you can also access archives on the website and YouTube channel. The SEG Traveling Lecturer Program was created to recognize excellent speakers who have made significant contributions to the field of economic geology and to support their participation in events relevant to the minerals industry, as well as for the SEG student chapters. They serve as ambassadors for SEG. Massimo will be presenting on the controls on the formation of porphyry, copper, and gold deposits. Massimo?
Yeah, thank you very much, Diane, and good morning to everyone. If you are in the States, and probably, I don't know, if there are people from elsewhere, good day anyway. So today I will talk about what I think could be the controls on the formation of porphyry, copper, and gold deposits, and especially on the endowments. We know that a big question, of course, also from the exploration point of view, is where and how and why these deposits form. But another significant question is to try to understand why do we have such a range of endowments in these deposits. For instance, here we have a supergiant deposit like Chuquicamata, more than 100 million tons of copper. And on the side, we have Bajo de la Lumbrera, which is only a few million tons of copper. So this would be equivalent to this in terms of relative size. And the same holds also for porphyry gold deposits, in which we have great disparities as well, with giant deposits like Grasberg and others which are almost devoid of gold. And in this case, this would be the relative ratio. So what I will try to address today is exactly this question. What are the factors which may control the different endowments of porphyry, copper, and gold deposits? And in the beginning, I will first focus on porphyry copper, and then I will shift to porphyry gold deposits. So my approach is very simple. From a theoretical point of view, it's quite simple. So first of all, let's have a look at a map of distribution of porphyry copper gold deposits. As you can see here, and as you know, we find them essentially at convergent margins, both in sin-subduction and in post-subduction settings. And here we have color codes which indicate porphyry copper deposits, porphyry gold deposits, yellow, and porphyry copper gold deposits in yellow with the green circle. So essentially, this is to show that the distribution is associated with this kind of two major geodynamic settings. So my approach, I was telling, is quite simple. We can arguably say that there are three main necessary ingredients to form these deposits. And these are metals, fluids, and ligands. And from a very simple point of view, we can say that the more of these ingredients there are, the larger is or should be the deposit. We know also from tens of years of studies, geochemical, geological, isotopic studies, that all these ingredients are mostly sourced by magmas. So my simple theoretical conceptual approach can be shown in this slide. I start from the end product, which is the endowment of the deposit, what is measured, and as we know, and then I go back step by step to try to reconstruct the processes and the controls on these processes to deposit such kind of endowments in different kind of deposits. So the first step going backwards is the fluid, is the magmatic hydrothermal fluid which precipitates these metals. And the link between the fluid and the final precipitation of metals is of course dependent on, in terms of amount of metal precipitated, is dependent on the fluid volume and on the metal concentration in this fluid, as well as on the precipitation efficiency. Now we have just said that this fluid is essentially magmatic in origin, so we can go a step backward and try to link the amount of this fluid to the magma. And here there are again a series of parameters. Of course, the amount of fluid will depend on the amount of magma and on the concentration of the fluid in the magma, and as well on the potential exsolvability of this fluid from the magma. And the amount of metal that it will carry, it will depend on the metal concentration in the magma and on the certain partition coefficients of these metals when the fluid exsolves from the magma. And now we can go even a step backwards, because now we are talking about magma volumes, and we can try to model these magma volumes using thermodynamic modeling with thermal constraints, and try to understand how much magma we can form in a certain amount of time. So all these processes are controlled overhead by the time. And there are two important time concepts, two time scales. One is the time scale, which determines how long a mineralization process is. And the other one is the time scale that determines how much time do we need to accumulate enough magma to liberate enough fluid which precipitates the observed amounts of metals. So, of course, this is conceptually simple, but maybe in the realization is not so simple, because there are so many parameters that have to be controlled that is quite difficult to control them all. So the approach that I used is a stochastic approach, so a statistical approach in which parameters are varied within reasonable intervals in order to see what are the most propitious conditions for the variation of these parameters within these reasonable intervals to form these deposits. And I would say that the most important parameters in the modeling are the copper and gold concentration in the magmas, the partition coefficients, the time scales that we observe here, and the fluid volume, which is strictly related with the magma volumes through the parameters that we have seen before. So before showing the results of the model, I will try to put some constraints, some geological constraints on these main parameters, starting from copper contents in magmas. So these are the results of several thousands of magmatic rock value taken from the literature, from arcs, and each blue diamond actually are median values of bind for interval of silica values. And we can see that in arcs, copper steadily decreases with the increasing evolution of the magma. And for typical intermediate felsic magmas, which are those typically associated with porphyry deposits, we can see that copper amounts are really normal. I mean, there is nothing exceptional. They are between 20 and 40, 50 ppm. Of course, this doesn't mean that there are no magmas which are copper enriched. This is always a possibility, but statistically, this is what we have to deal with. This is the major signal that we see in arc magmas. And the model is based on these amounts of magmas, on these amounts of copper in the magmas, to understand whether we can form still deposits with these amounts of copper and under which conditions. Timescales of magmatic activity, well, we have a few studies that have collected radiometric dating on magmatic activity, which is synchronous to the mineralization, but also precursor to the mineralization. And this comes quite evident that there is quite a long story of magmatic precursor activity in many of these deposits, which goes up to a few millions of years. And this is quite common. So this is another parameter to take into account. Timescales of metal deposition, so of precipitation of the mineral, of the ore minerals. Here things become more difficult, but I have tried to screen out the deposits for which most precise and accurate data are available. And we have a wide range of ages from a few tens of thousands of years up to almost 2 million years of duration of magmatic hydrothermal activity associated with the mineralization. And there seems to be also some kind of positive correlation between the duration and the copper endowment in these deposits. This needs to be validated by more studies, in my opinion, and we are working in that sense to obtain more data and to see whether this relationship holds true and what are the reasons of this scatter, whether they are due to inaccuracy of the ages, to missing data, to inaccurate data also of the endowment of the metals. So there can be many variables in there. Melt production constraints. To approach this problem, we have used one of the most used model for magma evolution and generation in arcs, which is the model of Andean et al., which is essentially based on a typical arc flux of magma coming from the mantle and injecting into the crust at different crustal levels. So this magma, which is basaltic in composition and has a temperature of in the model of 1280 degrees, will cool once it is injected at a certain crustal level until solidifying. But if we keep injecting the magma always in the same place, this magma will build up thermal anomalies in the host rocks, and eventually not all the magma will freeze down. And there will be some residual magma which will be initially rhyolitic in composition, which will stay. And through continuous injection, the composition of this magma will modify and shift towards to more mafic composition, not really mafic, but less felsic, let's say, up to intermediate composition. And of course, this process, at the same time, it will build up such a thermal anomaly that also some surrounding crust can start to melt and mix with the residual magma coming from the fractionation of the basalt, forming a so-called hybrid magma, which is the result of the mixing between the crustal and the residual magma coming from basalt fractionation. Because of the geothermal gradient, this process, of course, is much more efficient the deeper we go into the crust, because the crust is hotter, and therefore we need less energy to make all this process going on. The result of this, using the parameterization of Andean et al., is shown here. This is the duration of injection with an average fixed typical arc flux rate, and this is the melt productivity, where melt productivity is the sum of the crustal plus residual melt. And we can see that, as it can be intuitively understood, the melt productivity increases through time, of course, because we build up the thermal anomaly. And if we see now the color codes here, they correspond to different pressure at which the magmatic systems are accumulating. Blue are shallow depth, and pink are the higher depth. And of course, if we stay at one fixed duration of injection, the buildup of magma is much more important at higher depth than at shallower depth, because of this thermal constraint, which is dependent on the geothermal gradient. So you can accumulate and form more magma at deeper levels than at shallower levels. So we have introduced this as well in the model. We have also tried to put into the model some geochemical constraints. One of the most used or the most fashionable is the strontium-yttrium values. This is a compilation of Bob Laux of several copper and gold-rich deposits. And these bands here, red and purple, are the average plus minus 1 standard deviation of all these data, in which we can see that copper-rich deposits are in general characterized by higher strontium yttrium values, 100 plus minus 50, than gold-rich deposits, whose average is 50 and with a standard deviation of 25, so 50 plus minus 25. So we will, I will show you what for us is the meaning of this association. Well, how did we constrain these strontium yttrium values into our model? Well, the starting point is experimental petrology. Experimental petrology tells us what are the minerals which are fractionating at different depth in this model, as we have considered the model of Annen et al. And we have associated to these minerals appropriate partition coefficients for strontium and yttrium. And the results are shown here in these panels here at low pressure, intermediate pressure, and high pressure. So we can see that with the magmatic evolution, so decreasing melt fraction or increasing evolution, the strontium yttrium value decreases at shallow pressure, stays more or less constant at intermediate pressure, and strongly increases at high pressure. Another very important parameter is the water, which is contained into the melt, which is accumulated at different crustal levels. And in order to do this, we have used these controls of the water solubility in silicate melts, which depends essentially on two parameters, the pressure and the composition, which is shown here. Well, increasing pressure causes an increase in insolubility, so of the fluid, and the solubility of fluid depends also on the composition of the melt, being higher in felsic than in mafic melt. So all these parameters were introduced into our model that, as I said before, we used a stochastic approach in order to input into the model all the possible variabilities that we have seen. These are some of them, or some of the most important, which are shown here. And the next slide shows you the results of this modeling. In this plot, which in the y-axis shows the pressure of the magma accumulation, so the depth at which the magma is accumulating within the crust, and on the x-axis, the duration of the magma injection. The color codes here indicate what are the exsolvable amount of copper associated with each point in this space. So we can see that the blue points indicate fluids, exsolvable fluids which carry low amount of copper, and the amount of copper increases going through this light blue and then to the green and finally to the pink. So the most fertile magmatic systems are the pink ones. And we can quickly see that these magmatic systems are those which require a duration of injection of magma into the crust of at least 2 million years and accumulation depth of more than 15, 17 kilometers, so more than 0.4 gigapascal. So what does it mean, this? Well, according to what I said before, this is, again, intuitively quite easy to understand, perhaps. Here, these are isolines of melt volumes, of magma volumes associated with the modeling, which show that the increasing fertility of magma is accompanied by an increasing amount of magma, which is formed at this depth. And even a better concordance is with the increasing amount of water, which is dissolved in these magmatic systems. So essentially, this diagram tells us that these systems formed at high pressure and at after a long or relatively long continuous injection of magma are those which are most fertile because they are larger and they contain more water. What happens with the strontium yttrium? These are the result of strontium yttrium, again, divided for simplicity as isolines. So all the field here are for simulations for magmatic systems which have strontium yttrium values more than 150. All the simulation below this line are for magmatic system with strontium yttrium values less than 50, and in between are the simulation for magmatic systems which have strontium yttrium values between 50 and 150. So it is quite remarkable the fact that only between this interval, in this interval 50 to 150, which is exactly what Bob Laux has, from his compilation has come up with, is the one which coincides with the most fertile magmatic system. Of course, there are also systems which are not fertile in this range, but this range is the only one which is associated with the most fertile magmatic system. We will see the reason of these different degrees of fertility within this prospective or fertility range of strontium yttrium values. So what is basically the meaning of the association of strontium yttrium values between 50 and 150 with the most porphyry deposits? Well, according to our model, this is shown here. These are again the values of the simulations, strontium yttrium of the hybrid magma produced by our simulation, and these are the volumes of hydrous melt and the exsolvable water. Again, we see in another way what we have just seen before. This is the range of the natural porphyry deposit, or those which are the richest, and not only richest, but most economic porphyry deposits fall within this range. And we can see that according to our simulation, it's only within this range that we have the highest possible volume of magma which are produced, and the highest amount of water which are contained in these magmas. So this association is nothing else than a proxy that tells us these magmatic systems are forming in the right pressure and time conditions to develop fertile magmatic systems. So does our model reasonably match the reality? Well, this is a plot showing again now our simulations. The different color codes in this case indicate the point density. So blue are very low densities, so low probabilities. And the more we go to the warmer colors, green, yellow, orange, and reddish, the higher is the probability. So we can see again the shape of our simulations in this plot of endowments in the deposit and in our simulations versus the strontium yttrium of the real magma and of our simulations. And we can see that the real deposits follow quite nicely the same kind of triangular distribution which is shown by the simulations. Again, with the peak between 50 and 150. We can further explore this diagram, translating it into probability plots. These probability plots are vertical cross sections within these different three intervals, 0, 50, 50, 150, and more than 150, in which show as solid colors our simulations, our Monte Carlo simulations, and as the dashed red line, the distribution, the probability distribution of the natural porphyry deposits. And we can see that there is quite a nice concordance between our simulations and the natural distribution of the deposit. In particular, again, only within this interval of 50, 150, we can have some probability according to our model of forming deposits of the largest sizes, which is also observed in nature. And our model also agrees quite well with the fact that the greatest majority of porphyry deposits we find in nature are actually of relatively low tonnage. We can further show this data in another plot for which we can plot also natural porphyry deposits. This is a plot of the overall duration of the ore deposition versus again the strontium yttrium ratio of the associated magmas. again, we observe a good correspondence, and I would especially invite you to look at the color codes. Again, here the color codes of the simulation correspond to different potential copper endowments which are associated with the simulations, and they are the same color codes as the endowments measured in these deposits. So you can see that there is a good concordance between the color of the simulations and the color of the real deposits. Reddish here, greenish here, and bluish here, which is a witnessing of a good overlap between the model and the natural porphyry deposits. So summarizing, according to our model, to form the largest porphyry copper deposits, we need to accumulate large amount of magmas, and this large amount of magmas can only be accumulated at the deeper crustal levels and require a long accumulation time. So this is also quite in agreement with the fact that porphyry deposits form at the end of a long compressional history. And we think that this compressional history, actually, which precedes the formation of the deposit, is favoring the accumulation of magma at depth, preventing them from escaping towards the surface. However, these magmas at depth, of course, they cannot form porphyry deposits. We know that these magmas must ascend to shallower level in order to exalt fluids. And from our simulations, all these magmas are water undersaturated indeed. So we need a second step in which this magma is transferred from deep to shallow levels. And this transfer, as it is been shown by several studies, is probably associated with the tectonic switch from compression to more near neutral stress conditions in the upper crust. This could be the trigger for the transfer of the magma from the deep to the shallower level. And the build-up, a shallower level of incremental parental chambers, and from which we have the offshots which form or the fingers which form the actual porphyry mineralization. And this transfer of magma, of course, can be quick, can be short-lived, or can be long-lived. And we think that the longer it is lived, the longer it will incrementally build up the endowment of the deposit. And as it has, at this preliminary shows the correlation between the copper endowments in the deposits and the duration of the magmatic hydrothermal activity at these deposits. And also in terms of volumes, well, this is the drawing of Silito, and we, of course, our simulations are largely within and in agreement with the size of these parental magma chamber, which are incrementally constructed in several hundreds or up to millions of years, depending on the situations. So this is so far the copper story, but as I said before, we have also porphyry deposits which are very important for gold, as we have seen before. So what is the relationship between the two? This can be shown in this kind of two plots here. So in these plots, I have considered now all or most of the available porphyry copper gold deposits from various databases. In this plot on the left shows the relationship between copper and gold endowments of each one of these deposits. And on the right-hand side, we have a plot of where available the ore duration of these deposits and the gold endowment. And it comes quite clearly that there are two separate trends. It's like there is a dichotomy in the behavior of copper and gold concerning porphyry deposits. Two trends that we can say, or we can call them copper rich and gold rich, and these have been already called like that in the literature in the past, actually. So we can now put to each one of these points also some more information we can add. And in the next plot, the information that I have added is the kind of geochemical signature of the magmas associated with these deposits. This is shown here. So the green triangles are calc-alkaline magmas, and the blue squares are high potassium calc-alkaline to alkaline magmas. And again, we can observe some systematics in this case, because the copper-rich trend consists only of deposits which are associated with calc-alkaline magmas, whereas the gold-rich trends consist of deposits which are associated both with calc-alkaline and with alkaline magmas. And quite importantly, the 6 largest porphyry deposits seem to be associated with variably alkaline magma. And the same can be seen also in the companion plot, again, of ore duration versus gold tonnage. So I will try to come up with an explanation of this dichotomy and of this association. For the moment, one thing to hold in mind perhaps is that these deposits are associated with the thick crust, with typical calc-alkaline magmas and since subduction Andean-type settings, whereas many of these deposits are associated with thinner crust, island to transitional arcs, post-subduction to extension, although some of them are associated typically with calc-alkaline thick crust, since subduction setting. Another difference that we can observe, which was anticipated before, is the different strontium-yttrium values of gold-rich and copper-rich deposits, which is shown here. Again, the gold-rich are characterized by overall lower strontium-yttrium values with respect to the copper-rich deposits. And again, we can overlap here the information about the magma chemistry associated with these deposits. Again, the majority of the gold-rich deposits, or many of these gold-rich deposits, are associated with the alkaline magmas. So let's try to understand what can be the causes of this dichotomy of the two trends. And I will start with copper. So this is the same plot as before, ore duration versus copper endowment. But before, only the green points were shown. And now I have added here also the porphyry deposits which are associated with the alkaline magmas. So it seems that also with this addition, the trend is not disrupted. So it seems that all these deposits plot along a similar trend, which seems to suggest a similar kind of rate of copper deposition. So this suggests that the difference probably is not associated with the behavior of copper, but mostly concern behavior of gold. A different behavior of gold in these two kind of deposits. And in the following, I will try to find what could be this different behavior, to what could be associated with this different behavior, addressing 3 main possibilities. The possibility that there is a higher gold contents in the magma associated with gold-rich than the copper-rich deposits, that we have a higher or a different fluid melt partition coefficient for gold in gold-rich than in copper-rich associated magmas, and the final one, that there is a higher gold precipitation efficiency in gold-rich than in copper-rich systems. So let's start with the first possibility. So higher contents in the magmas associated with the gold-rich deposits. Indeed, we know from the literature that alkaline magmas contain higher amounts of gold with respect to calc-alkaline magmas. These are data from the literature taken from different studies which show that there is quite a significant higher amount of gold. These are the highest frequency of values, an interval of values for the 2 different kind of rocks. However, these are Monte Carlo simulations which show what are the amounts of exsolvable gold starting from either calc-alkaline systems or alkaline systems. And this black line here is Grasberg. Actually, it's the largest porphyry gold deposit. And these are the median and mean values of the simulations, which indicate that for calc-alkaline systems, we have a median mean values around 14,000 tons. So well above the endowment of Grasberg. Of course, alkaline systems are even higher, are about the double. But this plot tells us that in principle, we should be able to form gold-rich deposits also from calc-alkaline systems. And probably this tells us that this different kind of gold contents in alkaline and calc-alkaline system is not the only, or is not the main answer for the formation of these two different trends. So we can strike out the first possibility. At least it's not the main reason, even though we will see that it has an important role. So let's address the second point, different fluid melt partition coefficient in gold-rich and copper-rich systems. So again, this is our plot seen before. And I have used here again Monte Carlo simulations, which are shown by the gray dots, using typical literature partition coefficients for gold and for copper, starting from alkaline magmas and from calc-alkaline magmas. And the simulations in both cases are very similar, and you can see that they indicate that these fluids actually should be very gold-rich, much gold-richer than copper. So again, this doesn't seem to be an explanation, or unless these literature values are completely wrong, which is a bit unreasonable, as I will show you later. But another important thing that comes out from this plot is that our simulations here coincides very well with the copper-gold ratios for volcanic emissions and single-phase deep fluids of porphyry copper deposits and the field of calc-alkaline and alkaline rocks. So this basically tells us that these partition coefficients are correct because they reproduce very well what we directly measure in volcanic emissions and in single-phase porphyry fluids, and even in the rocks, suggesting that there is not much partitioning at the exolution stage between copper and gold with respect to the predicted values. Actually, we can shift our simulations towards a more vertical trend, only assuming unreasonably low partition coefficient fluid melt for gold of 1 in this case, or even lower, which is completely unreasonable. So, in my opinion, this indicates that also this is not the answer to the dichotomy of the two trends. So we are left with the last possibility, and I will show you now some simulations that I have carried out using the same philosophy as I showed you before for gold-rich, to reproduce the gold-rich and the copper-rich systems. And these are shown here. I will start with the right-hand side plot, which concerns simulations in gray, starting from calc-alkaline magmas. We can reproduce the two trends, in this case, the two distinct trends, by taking a better gold precipitation efficiency in the gold-rich deposits with respect to the copper-rich deposits of about a factor of 12. The interesting thing is that starting from calc-alkaline magmas, you can see that our simulations stop here, and they cannot reach the highest endowment of the gold deposits associated with calc-alkaline magmas. But they can explain all the gold endowments of the deposits associated with the calc-alkaline magmas. On the left-hand side is the same exercise, now starting from composition of alkaline character, therefore with higher gold contents. And again, we can reproduce the two different trends, assuming again a higher efficiency of gold precipitation, in this case a factor of 5, with respect to the gold precipitation in this trend. And the significant thing is now that starting from alkaline magmas, our simulations cover and reproduce also the richest deposit. So indeed, even though I said before that the different gold contents of calc-alkaline and alkaline magmas are probably not the main explanation, and is shown here, this plays an important role because apparently there is some petrogenetic control to form the gold-richest deposit, which are associated exclusively with the alkaline magmas. So what is the reason now of this different precipitation efficiency? Well, there is already a study about 10 years ago of Murakami et al., which had shown that there is a correlation between the copper-gold ratio and the depth of formation of porphyry deposits. So these are depths which are estimated from fluid inclusion studies from geological constraints. And this is the copper-gold molar ratio. In this plot, I just subdivided, I reproduced the same plot for copper and for gold. What is the difference here is the size of the circles which correspond to the endowment. So the largest copper deposits here are shown to be formed at depth which are higher than about 3 kilometers. And the largest gold deposits here are shown to be formed at depth which are less than 3 kilometers. The two colors, green and blue, indicate green again calc-alkaline and blue alkaline magmas. Interestingly, all alkaline porphyries are formed at shallower depth, whereas calc-alkaline porphyries can be formed in a range of depth from shallow to very shallow to deep. Another thing that comes out from these plots is that even though the largest copper deposits are formed at higher depth, there are also deposits which are very small, formed at the same depth. And the same is true also for gold. Even though we have large deposits only at shallower depth, we have also deposits of gold which are very small. So the control on this is the time factor that we have seen before, which is shown here for the case of gold, and we have seen before for the case of copper. So the longer is the time of magmatic hydrothermal activity, probably the more incrementally increased is the amount of metals precipitated. The big difference is that in the copper-rich deposits, the gold is added to a very, very low rate. This line indicates more or less the trend of these copper-rich deposits. It is an average of 100 tons of gold per million years. Whereas in the gold-rich deposits, this rate is much increased to 4,500 tons as a reference line. And the reason of this seems to be associated somehow to the shallower environment and to a decoupling, according to Murakami et al., to a decoupling in the behavior of copper and gold at deep and shallower level. I would like to make a final interpretation or a final discussion. These plots here on the right-hand side show some literature result which show the relationship between the strontium-yttrium values of arcs. So each point here is an arc, is a quaternary arc, average values for the bin interval of magnesium between 2 and 6 weight%. And this plot shows that there is a correlation between strontium-yttrium values within this interval of magnesium values and the crustal thickness. And this plot shows basically the same thing. So basically strontium-yttrium values, the higher they are, the thicker the crust in which this magmatic system evolved is. And actually they indicate an average depth of evolution of the magma. And of course, where the crust is thicker, in average, magma will forcibly evolve at average deeper levels than where the crust is thinner. So now, if we plot here the depth of formation of the porphyry deposits constrained by fluid inclusion data from geological constraint versus the strontium-yttrium values of the associated magmatic rocks, which is a completely independent way of constraining and indicates the average depth of magmatic evolution, we see that there is a correlation between the two. So basically, where the crust is thicker, the magma evolve at a deeper level in average, and also the porphyries seem to form at deeper level. And where the crust is thinner, the magma evolve at thinner level, at a shallower level, and also the deposit, of course, they must, occur above the site of magmatic evolution, and they evolve at shallower level. This is a field of investigation because it's not completely clear to me whether this relationship indicates is purely tectonic, geodynamic, or indicates a self-constrained behavior of magma associated with these two kind of crustal thicknesses. But basically, this seems to indicate that there is some kind of tectonic and geodynamic control. Thicker crust average deeper level of magmatic evolution, and in average deeper emplacement of porphyries with consequent copper enrichment and gold depletion, whereas the contrary happens whereas gold is enriched, let's say, where we have geodynamic settings or tectonic settings where magmas evolve at shallower level because of thinner crust, or because possibly also extension where the crust is thicker, like for some deposits of the Andes, like Maricunga belt, which is of course emplaced in a thick arc, but still they have been formed at very shallow levels, allowing the formation of these gold rich and copper poor deposits. So basically, to sum up everything, we have a situation for copper rich deposits which is favored by the buildup of large magmatic systems, usually at high pressure and for a long time, which is favored by long periods of compression probably. Then a switch to a more near neutral stress regime, which favors the leaking of the magma from the deeper part to the shallower part, with a more or less continuous transfer. And the longer is this transfer, the longer and the higher becomes the incremental construction of metal addition into the deposit. Basically, the same occurs also in the gold-rich deposits, only that everything is shifted to shallower level. And the shift to shallower levels prevents the buildup of very large magmatic chambers, which as a consequence, the fact that these deposits, although some of them are very copper, can be significantly copper rich, never reach the amount of copper which observed in this setting. But the counterpart here is that the shallower, overall shallower environment of magma evolution and porphyry emplacement results in gold enrichment of this deposit. But also in this case, it is important to underline that the higher endowments of gold are the results of an incremental construction through several addition of pulses through time. So I would like to conclude with this, that actually we see only this tip of the iceberg for porphyry deposits, but probably there is so much more to discover underneath. And I thank you for your attention very much, and I will be happy to take any questions.
Thanks, Massimo. And as a reminder to participants, you can submit questions using the Q&A button, which should be found in your control bar. And we'll plan to answer as many questions as time allows. And then with that, Massimo, I had an initial question dealing with the density of gold in comparison to copper, and that gold was denser. So how is it possible that gold is found in shallow depths compared to copper?
Well, according to Murakami, there is to several studies, there is a decoupling. Gold can be transported in the vapor phase quite easily. So usually it migrates up, and this is why also we find so much gold in the epithermal shallower environment, just because it is transported in the vapor phase very easily, probably more easily than copper.
Great, thanks. Have you tried to estimate the precipitation efficiency, assuming how much gold and copper there is available in the different magmas and how much there is in the deposits.
Well,
you might have mentioned it already, but he
yeah.
just asking for clarification.
Yeah, the simulations are based, as I showed you, on rough bins of initial gold and copper, different gold, especially because gold seems to be different in alkaline and calc-alkaline magmas. There is much less data from copper, but from what I have seen, I didn't see a significant enrichment of copper in alkaline magmas compared to calc-alkaline magmas. And this is the reason probably why all these deposits plot along a linear trend for copper, but not for gold. Oh, one of the reasons, at least.
I have a question about what tests you would recommend for intrusives that we have that are available for sheeted gold veins to determine the potential of intrusives to form a deposits, and then who would do those types of tests?
Well, this is if we enter in another kind of processes of formation of deposits which are slightly different, probably all the parameters have to be changed. So this model that we have applied is, well, it's a very generic model, of course. It's not, I wouldn't say that is the magic wonder which solves all the problems, but gives some idea of how these deposits can develop different endowments. Then to apply directly some how do you say, measurements that can tell you something, I think that this is a step forward which is not so easily done. For porphyry deposits, I mean, I have quite a clear idea that the duration, so high precision dating, trying to constrain the hydrothermal magmatic span is a very important thing, given and the strontium yttrium values of the rocks or the lanthanum ytterbium. I didn't talk about this. One problem is that the strontium yttrium, as many geologists working in the exploration, can be affected by alteration, whereas lanthanum ytterbium probably is more resistant. So I would say these two parameters, magmatic values of strontium yttrium, lanthanum ytterbium falling in the right range, and duration of magmatic hydrothermal activity, these can give, as I showed before, some even semi-quantitative ideas of what could be the size of the deposit.
Do you think there's any differences in the magmatic oxidation state that might have on the formation of porphyry copper versus porphyry copper gold?
Yeah, well, there have been some studies showing the existence of the enrichment of gold in reduced porphyry deposits. There are a few examples, and of course, this remain a possibility. This is dependent many times, maybe sometimes directly on the magma, but many times on the interaction of the fluid with country rocks, which are reduced. I think that this is a possibility that has to be investigated at local scale when these conditions apply for the occurrence of a control of the redox state. But most of these deposits, actually, they are all oxidized. All the deposit that, most of the deposit that I have included in my study.
Great, thanks. I have another question of what is the main control for the strontium yttrium ratio in melts, and is the garnet plagioclase ratio the determining factor?
Yeah, well, I worked a lot on this. Yes, of course, plagioclase is the repository for strontium. So inhibited fractionation of plagioclase will leave the strontium in the melt and will determine an increase of strontium. Yttrium is more complex. There are different minerals which can go, in which yttrium can go in. One is garnet, of course, is one of the one who likes best yttrium, but there is also amphibole, also titanite, And well, there are many studies. The problem, garnet, of course, can be stabilized in the magma at under very hydrous conditions and high depth. Of course, most of the time we don't see garnet. So this is always the problem, that there are very few magmatic rocks which show garnet, especially well associated with this deposit. So in many occasions, I think that just amphibole and titanite can play a role, but there could be some cryptic garnet crystallization at those depths is completely possible, and experimentally it has been shown that it is possible.
So I have a somewhat related question. How useful is distinction and, how useful to district and regional exploration are the ratios from the altered wall rock?
Yeah, exactly. This is what I was saying before.
Yeah.
This is, yeah, strontium-yttrium has become very fashionable, but mostly applied to fresh rocks, but also in the compilation of Bob Laux, there is strontium-yttrium. Probably, I think, because mining companies, when they do the packages of analysis, they, maybe because of economic cost or because of the methods, they don't do rare earth elements. And so there is a much less database with the rare earth elements for all these deposits. Whereas there is a large database for strontium-yttrium because these elements are routinely measured by XRF. Whereas to measure rare earth, you need ICP or INA, or which is a different method. So yeah, of course, it would be very good to have an increased amount of measurements for all these deposits using elements which are less prone to alteration. But I have done simulation that I didn't show with lanthanum ytterbium, and for the few deposits for which there is lanthanum ytterbium available, we can observe also a good correlation, but I didn't show because there are only 3 or 4 deposits, so it's not very statistically significant.
Thanks. I have another question. There are gold-rich copper porphyries and a few gold-only very low copper deposits. Are these unique, or do they still follow the gold efficiency interpretation?
Yeah, they follow exactly the same trend. Absolutely. I worked, for example, in one of these few gold only. One of these is Kishlada in Turkey, and we worked on this deposit where basically there is no copper, and it falls exactly on the top of the trend that I showed before.
Do you have any thoughts on or explanations, potential explanations on the high gold endowments of a number of low K systems, such as in the far southeast, Panjua, I believe is.
Yep. Batuja, yeah, Panguna, far southeast, yeah. These are deposits which are associated with typically calc-alkaline magmas, not high potassium, so low potassium, as is, which the only thing that put them in common with the alkaline system is the shallow level of magmatic evolution and emplacement. So I would say that the only common point there is which causes the decoupling is this shallow level, which is associated with a setting which is essentially an island arc or with intermediate crust thickness. And under these conditions, probably there is enough energy to build up an important magmatic chambers, and there is enough thin crust to allow for this decoupling between gold and copper. This is what I can think of. And our simulations, they show that we can explain this calc-alkaline system through this decoupling, actually.
Great. There's a question related to, is there any data on the causal relationship between the age of a porphyry deposit and the stage at which the subduction is, as in, is it young or mature? And there's some background going into that question, as at present there seems to be a connection between the ongoing subduction compressional tectonic setting and the existence of large copper porphyry deposits. However, with ongoing subduction, the stress regime in the above mantle will likely gradually switch to extensional. And then just curious if there's any relationship between the age, the porphyry deposits in this stage.
I've carried out a study at Yanacocha. We did a very high precision dating, uranium-lead dating of the different porphyry or the different magmatic pulses which preceded the onset of the mineralization, and then during the mineralization, which lasted for quite a long time. And we saw that the onset of a change in the geochemistry of the magma coincided with the arrival at the trench of the lost Inca Plateau. This is a study of Rosenbaum, this one, who based on the mirroring of plateaus in the Southwest Pacific, he thinks that there is a mirror of the Inca Plateau, which is now subducted under Peru, and he reconstructed the shift or the travel of this Inca Plateau towards the trench, and it coincides exactly temporally with the switch that we observe, the onset of high strontium yttrium values in the magmas, and then subsequently of mineralization. And other studies in other study, Rosenbaum also showed that this is quite systematic for the deposits of the Andes. Cook also, he talked about this in his paper in 2005.
So is there an influence if it's a flat plate versus a steep plate subduction versus a slab tears, and how do they influence the magma type, depth, and formation in order to predict the regional prospectivity for the copper versus copper gold versus gold rich porphyries?
Yeah. I would say, yeah, at a larger scale, there is absolutely a control on this. There is a nice study for Anatolia by Rabbi Roll, who shows all the control of slab rollback and of slab tear on extensional tectonics in the upper part of the crust, and the mineralization, which is in most cases gold rich, the formation of porphyry gold deposit like Kishlata, the one that I was talking before. And for the Andes, I think there is quite a large amount of data showing that these the largest porphyry deposits are preceded by these long periods of compression, and then a change to near neutral stress, like the studies of Tosdal and Richards have shown in different cases.
Great, thanks. I have a question related. What if you think silver-rich copper porphyries would have a similar story to the gold-rich?
I didn't investigate much this problem. I would guess that, yeah, silver and gold would have a similar behavior, but I didn't investigate this. I'm working a bit on molybdenum now, but silver, I'm not yet there.
What is the relationship or connection between the porphyry and epithermal endowment?
Sorry, which is the question there?
What is the relationship or connection between the porphyry and epithermal endowment?
Well, in theory, probably the gold-rich, the copper-rich deposits, which are formed at depth, they are formed by fluids which precipitate copper at depth, and eventually these fluids escape towards the surface to form, in theory, epithermal. They could form epithermal gold-rich deposits. So then it depends, of course, on the level of erosion of these deposits, if they are still preserved or not. Whereas those formed at shallower depth, copper and gold co-precipitate, and therefore there is no such decoupling.
Great, thanks. And Massimo, we're after the hour mark, and just to be mindful of everybody who's listening, I think I will leave it there, even though we've had some great questions. And I wanted to thank everybody, and thank you, Massimo, for your presentation, and to everyone who's attended. And then just as a note for everyone, here is Massimo's contact information if you have any follow-up emails. And then as a reminder to folks, when you're leaving the webinar, we have a survey, and we would appreciate your feedback to help us learn what went well and where we could improve, as well as some ideas for future webinars. We look closely at this information, so I really appreciate that. And then with that, thank you again, and this concludes today's webinar. Bye.